I'm Michael Perez, and welcome to the Michael Perez Podcast, a place where I think out loud, sharing the topics that matter with those who want to listen. Here, I journalize my scientific adventures. Today's podcast, I will be interviewing Landon Curt Noll. The first complete sentence Landon spoke at the age of 2 was, "How far is the sun?" Landon remains an astronomer to this day, where his study is focused on the inner solar system, the zone in which we ride our wonderful planet. As Cisco's resident astronomer, Landon focuses on the balanced technical computing by day and our inner solar system as an astronomer by night. Landon has made astronomical observations during total solar eclipses from every continent and ocean on Earth. He served as the expedition scientist for a team that searched for meteorites in the Antarctic ice and near the South Pole for a number of years. Landon Curt Noll is the N in the widely used FNV hash. He's also the founder of the International Obfuscated C Code Contest. He was a member of the working group that developed the IEEE POSIX standard. He participated in the IEEE 1619 development of XTS and co-authored the XTS AES Cryptologica paper on the security of ciphertext stealing. He serves as chair in the Cooperative Computing Award Advisory Panel to the Electronic Frontier Foundation, advising them on awards for the discovery of astronomically large prime numbers. As a mathematician, he developed or co-developed several high-speed computational methods and has held or co-held 8 world records related to the discovery of large prime numbers. He is credited in Wikipedia as the co-inventor of a system for naming numbers of any size. Landon graduated from Linfield College with a bachelor's in mathematics and physics. He is a member of the American Mathematical Society and is an associate of the American Astronomical Society. Before listening to this podcast, I recommend you read up on the preface section. There I break up all the concepts and terminologies I'll be discussing, and they're all neatly organized. This podcast's topic can get moderately technical, so reading up early might be useful. If you'd like to follow me on social media, my Instagram is @mike.514. My Twitter is @Mikey Perez, my Facebook is @TheMichaelPerez, and my LinkedIn is simply Michael Perez. If you'd like to support this podcast, even a cup of coffee can go a long way. Simply visit my website and click on the support link. Given the scope and duration of Landon and I's conversation, I've decided to break up this episode into 3 separate podcasts. Without further ado, I present Landon Curt Noll. Landon, welcome to the show.
Thank you very much for inviting me on. It's a pleasure to talk with you and your audience about prime numbers.
Yes, amongst the many things you've done, but we'll just focus on prime numbers today. So I'll get right to it. The first question is, what is a prime number?
The definition I like to use is it's a natural number, like 1, 2, 3, 4, 5, is prime if and only if it has 2 distinct factors, namely 1 in itself. So, for example, 2, 3, 5, 7, 13, 17, so forth are some of the first primes. 6 is not prime because it's actually divisible by 2 and 3. One thing, by the way, people often ask us, and what about 1? And we typically don't define 1 as prime by definition. There was actually a period of time between about the mid-18th century and the start of the 20th century where there were a number of people who referred to 1 as prime, but that has fallen out of fashion due to the fundamental theorem of arithmetic is cleaner when 1 is not prime. So we essentially say 1 is not prime by definition. So you might say a prime number is a number greater than 1 that has only 2 distinct natural number divisors.
So apparently that's not a question you want to bring up at a number theorist house party. Seems like there's a lot of debate between.
It turns out in the history of 1 not being prime, there was actually almost no one on record referring to 1 as prime until a mathematician named Stevian in 1585 was the first one to sort of consider 1 to be prime, and it became fashionable between the 18th and 20th century. But you might say, what is a mathematical definition? And a pragmatic answer would be the mathematical definition is something that mathematical community agrees upon. We define 1 to not be prime, and the usual excuse as to why is because of the fundamental theorem of arithmetic. That's actually an important thing that primes are related to. where any natural number can be expressed as unique, ignoring order, product of primes. So like 1400 can be expressed as 2 times 2 times 2 times 5 times 5 times 7. And that's a unique products that make up 1400. If you made one prime, then you could say 1 times all that stuff is another product, and 1 times 1 times 1 times all that stuff could be another product. So by assuming 1 is not prime, fundamental theorem arithmetic is a much more simple thing to state.
Exactly. That makes a whole lot of sense. And what I've noticed is looking at the largest known primes, including yours, I know you've held several world records, each one of those primes were Mersenne primes, that being to the form of 2 to the n minus 1. Is there a particular reason for that? Or are the algorithms more friendly for discovering such primes? And what are the other classifications of prime numbers?
Mersenne numbers are 2 to a power minus 1, or 2 to an integer power minus 1. And I guess when you're talking about primes, you typically, by default, you're talking about integers, but 2 to an integer power minus 1, and that power being greater than 0. So there's a fairly elegant, easy to understand test. It's called the Lukas Lamer test. And it's relatively easy for people to code. Recently, there have been people that have built a set of programs that allow people distributed around the internet to go and try 4 primality tests. So that's been sort of a fairly popular method. It turns out there actually are easier ways to find a new largest known prime. But the software that's out there and the community that's built around it has been focusing on the Mersenne primes, and they're historically interesting as well.
And for the listeners, the Lukas Lamer test is a primality test. It's a definitive test which determines if a number is prime or not. For smaller numbers, you can simply just check if any number less than the number you're looking for is a factor of the number you're looking for. Obviously not including 1. And if you want to be clever, you can just check every number less than the square root of the number you're looking for. And for bigger numbers, you can use something called the Lukas test. It's a non-definitive test. And in this process, you use something called Lukas sequence numbers, which are very similar to Fibonacci sequence numbers. And this test gives you one of two results. Either the number is definitively not a prime, or it's something we call a Lukas pseudoprime, where it's very possibly a prime, but you have to run another confirmation test. And sometimes these confirmation tests require a lot of computational power and time. Next is the Lukas Lamer test, and this is the test we're leading up to. And again, this test definitively tells you whether a number is prime or not. This test uses numbers from the Lukas Lamer sequence, and these numbers are built exponentially off of the number before it. So you can imagine these numbers grow really, really big, really, really fast, and there you have the computational complexity. It's why we can't easily determine whether any number is prime or not.
Yes. Yeah.
And for the palindromic primes, those are primes that are essentially, you can read them forwards or backwards, and they're the same value. Is there anything particularly interesting about those or elegant? And does that symmetry kind of help in the discovery of it, or is it just something that people fascinate over?
It's a mathematical curiosity, and there are many different types of primes that people look for. There's a fairly good site of prime number stuff that is run by my friend Chris Caldwell, and he has actually on his site a number of records that are for primes of the form factorial plus 1, or primes of the form h times 2 to the n minus 1, and so forth. He has a number of things that they keep track of. But certainly palindromic primes are one of those things that is interesting to consider. And you can ask questions about the distribution of palindromic primes or whatever other type of number that you'd like to talk about.
So how many prime numbers are there out there?
It's an infinite number of primes. There is no largest prime. There certainly is a largest known prime, but there's no largest prime number. You can always find a bigger prime number.
Yes, and as you know, that was proven from Euclid, and it's one of the most elegant proofs in mathematics, and maybe you can quickly walk us through that.
The method I like to talk about, and there's many ways to show the different number of primes, but let us assume that there's a finite number of primes. There is a largest prime, right? Assume that A is the product of all those primes. Let P be a prime that divides A plus 1, right? Because it can't be prime. So it has to be divisible by some prime. Since P divides A, because A is a product of primes, and P divides A plus 1, therefore P must divide 1, which is impossible. So that our original assumption there's an infinite number of primes is broken.
Yeah, that's an awesome proof, and that's proof by contradiction. I kind of read a slightly different one, but yeah, they're both fascinating.
Yeah, which one do you like?
It's kind of similar. So either there are an infinite amount of prime numbers, or there are a finite amount of prime numbers. And we assume there are a finite amount of prime numbers, and then we let x equal to the product of every prime number plus 1. And then we go ahead and try to divide x by any of these prime numbers, and whichever one you choose, you'll always have a remainder of 1. It would never divide evenly. So you're forced to make one of two conclusions, that either x is a prime number, and we're done, or x is a composite number. But if x is a composite number, its prime factors are not in the list, so the list isn't complete. And then you would add x to the list, and then repeat this process infinitely many times, concluding that there are infinitely many prime numbers.
Yes, yeah, right, and it never grows. So that's a different way of doing it, but it accomplishes the same thing.
Yeah, they're pretty much the same thing, exactly. Cool. And can you elaborate a little bit on what the prime number theorem is?
So, prime number theorem that talks about the number of primes less than x, right? It's a function we call pi of x. And one of the things that's been interesting for people is in terms of what are the distributions and how many primes are less than x. And probability of a number being prime is approximately the log of x. 1 over log x, excuse me.
Gotcha. So it ends up kind of tapering off asymptotically, right?
Yes.
Yeah, so you've got a whole bunch of prime numbers at the very start, and as these numbers get bigger and bigger, you're finding less and less of them, but the pace at which it decreases slows down.
Yes. So the probability of a random integer being prime is approximately 1 over the natural log of that number. And Gauss had approximation, an integral, that sort of approximated what pi was. Later on, this guy named Riemann came up with an exact formula for that. And it was an amazing result because it brought in something called the Riemann hypothesis and prime numbers and so forth. And it's one of those things where, again, we find that prime numbers are deeply rooted in surprising corners of mathematics.
Yes, and is the Riemann hypothesis one of the millennium problems?
Yes, I believe so. There's several, but it's one of the ones where the truth or falseness of the Riemann hypothesis or the extended Riemann hypothesis is one of the most wanted things within number theory. There's a lot of things that are resting on or waiting for that thing to be determined. There's a very deep thing of this zeta function, these infinite reciprocals numbers, that the zeros of these particular things have a deep association with prime numbers themselves and the distribution thereof.
So Fermat's last theorem was the one that had all the attention out of all the millennium problems, and now that that's been solved, I think all the attention has kind of moved down to the Riemann hypothesis, and it'll be the hardest way to win $1 million. But if you want to become a millionaire, that's one of the ways. What's the relationship between the Riemann hypothesis and the distribution of prime numbers?
The Riemann hypothesis has actually a fairly deep relationship, it turns out, and quite surprising, between zeros of a function, when a function evaluates to 0, and prime numbers. But you have to start off with saying, well, what is the Riemann hypothesis? It's a conjecture that this thing called the zeta function has zeros only either at negative even integers in the complex plane or in complex numbers with a real part being 1/2. And the ones that are on the even integers are called the trivial zeros. The complex zeros are the ones on the line. So if you plotted the Riemann zeta hypothesis and noted where it was 0 in a complex plane, so x would be the real numbers and y would be the imaginary numbers, the hypothesis states that the non-trivial zeros that are found between where the real part is between 0 and 1 only lie along the line of 1/2. And if that is indeed the case, if that turns out to be true, then Riemann has an exact formula for the number of primes less than x. Now, so what? Well, if I had an exact formula, I could tell you exactly how many primes were less than x. Then all I have to do is calculate that formula for different values of x. And when I find the formula goes up by 1, I got a prime.
Yeah, and for the listeners, if that doesn't blow your mind, I don't know what can.
Yes.
I mean, the relationship between these two is truly, truly mysterious and absolutely fascinating. And again, I believe the Riemann hypothesis as well is a millennial problem. $1 million to those who can solve it, which again might be the hardest $1 million you've ever earned. And I think a lot of people are trying to find zeros outside of that range, right?
Yes.
Yeah, isn't it one of those things which sound like it's easier to be proved by contradiction? So by showing that the zeta function does return a zero in places that are outside of those two number lines, where the negative number line on the whole numbers and the half number line on the y-axis.
Yeah, so finding the counterexample has so far failed. It doesn't mean that it might not exist, but it at least is pretty good. I mean, another thing that's really nice, the zeta function, the zeros give you the where to fix Gauss's logarithmic integral function and allow you to make it exact. And at that point, you could find primes through the Riemann hypothesis.
It puzzles me how certain numbers, which we seem to crop up everywhere, like pi, and it's somewhat telling that there is an underlying system here that we haven't really identified. Like for pi to crop up in random places, it almost seems to suggest more about us discovering concepts in mathematics rather than inventing them.
Yes, pi is certainly involved. The value of the zeta function at 2 is pi squared over 6. What does that mean? Well, if you look at the sum of the reciprocals of the squares, so 1 over 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared out to infinity, that turns out to be pi squared over 6. There's another interesting thing. If you look at the zeta function of -1, that turns out to be -1/12. That's why some people say, well, you could pretend that the sum of the integers out to infinity is -1/12. Well, that's not quite true. The zeta function at -1, which would be the sum of the integers, evaluates to -1/12.
Yeah, and that's it's quite a remarkable result, but you have to be very clear about how you construct such a statement when discussing that result, -1/12. You can easily, poetically, and socially engineer such a statement to be nothing but misleading. But this number does mysteriously crop up in mathematics and physics quite often, including areas like string theory.
Yes. There is here a really nice, I'll post it in the chat here. There's a really nice thing on the zeta function and on Wikipedia that's fairly correct. And, there are essentially fun stuff, like, for example, the zeta function at 0 is -1/2. The zeta function at infinity is 1. So it has some really interesting properties there, but it's bound up in the notion of primes and how the number line is constructed, and in surprisingly deep ways.
The Riemann hypothesis is so fascinating that it truly warrants a podcast in itself. And the extended Riemann hypothesis gets into a lot more complex stuff and has relationships with prime numbers, such as the density of prime numbers, but perhaps another time we can discuss that. And there you have it, folks, the first part to the 3-part series of this podcast. Of course, leave me your thoughts in the comment section. Let me know what you like, what you didn't like, and be sure to listen to the other 2 episodes. I feel like this episode was more introductory, and we delve into a little more of a philosophical conversation on the episodes to come.